Hi, this is Jonathan Gardner. I'm covering section 3.44 of Griffith's Introduction to Electrodynamics, second edition. This is actually the last part of chapter 3, so I'm excited. I'm going to go fast, but you can always rewind. Thumbs up and share if you like what you see. As always, questions can go in a video response or comments below. Let's get started. So the electric field of the potential of a dipole, so the dipole term. Well, this is going to depend on r and theta. Okay, so we're going to have, he writes it out this way, r hat dot the dipole moment divided by 4 pi epsilon naught, and we have the r squared, the distance from the origin there, squared. And we can rewrite this as p cos theta, where cos theta is the angle between the, what does they have there? Cos theta is the angle between the dipole moment and the direction to the point that we're interested in, divided by 4 pi epsilon naught r squared. So let's calculate the electric field, and the way we do that is we use a simple formula. V is equal to negative the E is equal to negative the gradient of V, and that's going to be a vector. Okay, so we're going to do this in spherical coordinates. So you have to turn to your inside cover of your book. Okay, so for spherical coordinates, we're going to have the r component of our E vector is going to be dV by dr. That's pretty easy. The theta component of the vector is going to be d, and I screwed up, 1 over r, d by d theta of v. And the phi direction is going to be 1 over r sine theta dv by d phi. Okay, let's crunch some numbers here. So the potential does not vary. Oh, it does vary actually. They're in the bottom. So we have basically 2 over that. So 2p cos theta divided by 4 pi epsilon naught r cubed. So we had -2. It cancels the negative sign. We should be very specific about where the negative signs go, so we don't confuse ourselves completely. Okay, that's the r component. Okay, the theta component is also pretty easy to calculate. It's going to be -1 over r of dv by d theta. Well, it varies by sign. That's a negative cosine, so it's negative sine. So we get negative p sine theta all over 4 pi epsilon naught r squared. So we get p sine theta all over 4 pi epsilon naught r cubed. Oh, it looks awfully similar. And the phi direction is equal to there's no variance in phi, so the answer is 0. It's a big fat 1 and 0. Okay, so we have our new electric field calculated using the gradient of the potential there. E vector is equal to, well, both of them have terms of 4 pi epsilon naught, p 4 pi epsilon naught. Both of them have r cubed. And so one has 2 cosine theta in the r hat direction, the other has sine theta in the theta hat direction. Okay, what does that look like? Remember, quadrupoles go r4, octupoles r to the 5th, and monopoles r just 1 over r. R squared, as you'd kind of expect, because you have to differentiate, and this is always going to increase by 1. But anyway, so the electric field goes by 1 over r cubed. The actual field, what it looks like when you have a pure dipole. Let's draw it this way, and then we'll leave some room over here for a physical dipole, and I'll kind of show you the little trick here. So this is a pure dipole. I believe this is when we have our p pointing. Let me just look at the picture they have in the book. So it goes straight up. Cosine theta is 0 when it's straight up. Yeah, and sine theta is 0. No, the cosine theta is 1, sine theta is 0. So our P, I'm going to draw our P here in purple, is pointing straight up. Okay, so what do the vector lines look like? Let's use a nice orangey. Okay, so field lines above and below just go straight up, and below it just, so there's like an electric field that goes straight up. There's something pulling you up. If you happen to be aligned directly with that P, you're going to be pulled in to the dipole. If you're off center, then there's like this loopiness that goes on here. Okay. This isn't exact. You can plug it into your favorite program and you can calculate what these field lines really look like. Basically, it's like a butterfly wing, and some of these go out, almost all the way to infinity. They come in from infinity. Okay, so if you put your positive charge over here, it's going to get sucked towards the origin. Whatever origin it is you choose, it's going to get sucked towards it. If it's out here, it's going to be pushed away from the origin. Whereas over here, it's going to be pushed straight down, as well as over here. So sucked in, if you're over here, you get sucked in. Over here, you get pushed down, you kind of wrap around. So that's what a pure dipole looks like. A physical dipole, if we actually calculated the potential for a physical dipole, and I'm just going to draw the two charges here. Let's use a purple. So we have our plus here, and we have our minus here. This is a physical dipole, and I might have drawn it too close to the page, but that doesn't matter. So we have a field line that extends like this, one that goes like that. These are all pointing up. And did I screw up? No, that makes sense. The negative closer this way, so you get sucked towards the negative and push away from the positive. Okay, it's the book that has it backwards. No, they can't possibly have it backwards. This has got to be right. Plus, it goes from the plus to the minus. So in between, it's pointing down. Yes, that's right. And then it starts to do this. It starts to do the bubble thing. Book was right. I was wrong. That's the story of my life. Okay, there we go. That's kind of what it looks like. Now, at first glance, you're like, okay, these look similar, but they're not the same. But when you take your finger and you cover up the center there, you kind of notice that these two guys really do look very similar. That's just testament to the fact that the farther you go away from the origin, the more a dipole behaves like a pure dipole. The more a physical dipole becomes like a pure dipole. So anyway, that's the end of chapter 3. These dipole business is going to become terribly important as we explore chapter 4, which has to do with how electric fields behave in actual matter, besides the ideal conductors that we've talked about so far. So I hope you join me for the next chapter. Hope you have a good day. Thanks. Bye.